All right, part two, day 57, I think we're on. There's the expectations, same first sentence, and then including real world applications. Another example of this idea of having a polynomial equation that's kind of a mess before we factor it. So we have to expand. And then move everything onto one side. And then we start factoring. It doesn't factor by grouping, so I'm going to use the factor theorem, call this f at x. And we got to find some factors, so f at 2 works. And how fast did I find that, right? Yeah, a little bit fast. I realize that I just read it right off my notes, and you don't have your notes there, but you get the idea. X minus 2 is a factor. And then it's the same old story, right? Once we know to expand and put everything on one side, it's exactly like the ones we did a couple of days ago, so this isn't too bad. Long division. Multiply by negative 6x, subtract. Same old now. Doesn't seem like there's anything interesting about this one compared to the last one, but let's just keep going. So what does this say? It says this becomes x minus 2 times x squared minus 6x plus 8 equals 0. So that, I see x equals 2, and this hopefully factors. If not, we could use the quadratic formula, and some of you, instead of factoring quadratics, might skip right to the formula, but I think this factors. I think it's minus 4 and minus 2. And it doesn't appear like there's much going on here, except for there's a copy of one of the solutions. It's kind of like a double solution here. Well, what does that mean? Well, we know that in the polynomial functions that when we had a double root, looks like this, doesn't it? That this function would have a bounce there. It means it's a double solution, but it still just means the solution set is 2 and positive 4, just 2 solutions instead of 3. And we shouldn't be too surprised about that. And if we wanted to have a look on the graphing calculator, again, I could put this equation in, or I could put in this equation and that equation. But I'm still thinking that there's only going to be 2 solutions. So I got x squared plus 20. And notice that this is a cubic, right? Degree 3. And this one, the right side, is just a parabola, right? There's no x cubed over here. Plus 2. And I'm going to graph that. Change that to 20 like it's supposed to be. And I should find 2 solutions, one at 2 and one at 4. And I should see a cubic crossing with a quadratic, and this is, I'm just checking it, even though I wasn't asked to. I'm doing it anyway. Zoom 6. Oh, there's the cubic, I guess. Oh, that's right, I goofed up my windows last time, didn't I? Oh no, I didn't. Let's I can't see much of this at all. So what's going on? Well, it looks like perhaps one of the, we're going to have to change the window settings. Well, let's zoom way out so we can see what's going on. Let's go down to negative 100 and positive 100. Go up by tens, and maybe we can see what's going on here. Ah, at 2 and at 4. And if I tried to find the intersection points between that graph and that graph, get over where they look like they're on top of each other. 4 and 144. But again, the y value we don't need. Right? Dandy. So this is the check. And notice, for that check, I graphed the left side. Y1 was equal to this, and Y2 was equal to like this. And I just looked for the intersection points. I could have graphed Y equals that, and that would have shown me the bounce there. That would have shown me that bounce if I would have graphed that. But, oh well. On we go. Example 2 is one of our examples of one of these real life situations, and this is the population of a town in hundreds. We actually have used this example last chapter, I believe, and maybe this came from a regression equation, right? The quad reg or quartic reg, actually it's a degree 4, starts low and ends low, so we might be expecting something that looks kind of like this, right? Some sort of M shape, starts low, ends low because it's quartic. But we want to find out when the population is 4,000 people. Notice that we got to be careful here. I'm going to change my color. 4,000 is when PT is 40 because it's already in hundreds, right? So that's when PT is 40. So the question is when is this graph equal to 40? We want to solve now. How are we going to do that? Well, I'm thinking, and I bet you're thinking the same thing, with all these decimals and all this exact, you know, these exact decimals in here, and wanting to find the exact spot where it's equal to 4,000 people, maybe we'll turn to technology. And again, there's two ways to do this. There's two ways. I could write the left side in here. Right? I could make this y1 and this entire thing y2. And then I would look for the intersection, right? Or, and this is just because I did it the other way last time, I'm going to move the 40 over to this side, make that 0, subtract 40 from both sides, and then I'm going to look for the x-intercepts of the graph. So I'm going to graph y equals this whole long thing. And see when this function here is 0. But there's, I could do it the other way if I like. And that's kind of up to you. Notice I put in an x instead of t, and that's all good. T to the exponent 3. Hate when it does that. Minus 33. That's supposed to say 33. And what's going to be some decent scale? I can't remember how far this goes out, but this is, no, it's not going to have to get up to 40 because I'm interested in the roots. So I'm going to just press zoom 6 and hope for the best. Taking a long time, taking a long time. Nothing. So that's no good. Maybe I'll zoom out. Okay, I'm going to zoom way out and have the y minimum population can't be negative, so I think that's probably okay. This minus 33 seems strange, but maybe I'll zoom out that way too. I'll go out to 50 there. And maybe this will be 50 as well, and graph it, and hopefully we'll be able to see some graph. Oh, there she goes. When does it equal 4,000 people? Well, it doesn't look like it's ever going to equal 4,000 people because the graph never hits 0, does it? Unless I type something in wrong, which is certainly possible. Let me see. Negative 0.1, negative 0.5x cubed, plus 0.4x squared, plus 10x minus 33. Subtract 40 from both sides is minus 33. Yeah, well, you know what? Maybe it's never going to be 40,000. This one has no solutions. So I'm going to take not take a screenshot of that one. Take a screenshot of this. Edit, paste that in there. So I say from the graph, since there are no x-intercepts, the population is never 4,000. It never got up that high. And from what I remember from the question before, that was actually I think that was true. It never actually got up that high. Now hang on, I did goof something up. Oh no, that was supposed to be a plus. Why didn't you stop me? Why didn't you stop me, people out there? Okay, let's fix this up. Graph. Oh, now there's going to be solutions all over the place. Oh, that looks better. Okay. Well, that was bad, wasn't it? Sad face. And now we can find the solutions there, right? So where it does equal 0, that's where we're going to find when the population was 4,000. So let's check it out. Go to the left, go to the right. .6 is that one. And then again on the way down, 6.7. So the x-intercepts are 2.6 and 6.7. So what years are those? Well, that's the years from the year 1900. So the population would be 4,000 in almost 1903, and almost 1907. Okay, and then was on its way down. Now you may be asking, you may be wondering to yourself, why didn't Mr. Restall just do this video over again? Because he made such a huge error and he's wasting my time. Well, this is the wonder of this sort of thing. I want to give you a real classroom experience, and if I were teaching this in real life, I would be making mistakes all the time, and I wanted to share that with you. So there. But that's a fun example, and notice we just use the calculator and skills that we're used to. Okay? Have fun with the calculators and have fun with that. Thanks for stopping by.